And then when you wanna see, let me show you. Here, right, in settings, you can see it has only 39% battery. So you have to make sure to plug it. Then, if you do audio and video, this is how it always should be. Speech mode, noise cancellation. With audio and that's and anything you should just stay. And then if you wanna like control the volume, this is how it. But usually you can see the intensity of the audio usually a little bit less than the middle, which is fine, but you can monitor it. And again, if you want to go to a wider shot, you go like this, just switch it, or you can click here. Perfect. Yeah, that's it. Here you can get the number of over here, and the comments, live comments will pop up here. That's once you finish. You hit here again.
If you can stop and start, yeah.
And you hit again, slide, and it will tell you, do you want this to stop streaming? Yes.
Okay, perfect. Thank you.
Yep. Let's connect this. Oh, this is it. Okay, cool.
This is actually, we can check, but I think it's really loose, so I will just extension cable.
It is working because it has it, but if you want...
Yeah, I'll switch it because it's really loose.
Okay. So are you
Yeah, you're perfect. Does the Mac have the charger for the iPad? Otherwise, I can get my iPad.
Yeah, sorry. Yeah.
I will sit in the bathroom.
Generally functional I think what I would suggest to you is, like I'm fine, so I'm fine it's not a big deal. I don't really expect people to do it, but I do expect people to understand. We talk about this live and it's going to be super interactive. Yeah, exactly. I'll give you an introduction, and then like, there is a tutorials page that leads to goes through that ahead of time. Basically, what happens is 6 weeks ago, we have so you find the tests, but the question is like how personal it's just like is it easier? Well,
Here we got just got I call science. Just switch it on.
Welcome everyone. I'm Alex Lex. I'll be your instructor this semester. We'll be talking about visualization. So everybody in the right class? Great. So for whom is it the first semester here to you? Wow, lots of you. Welcome. Who are the undergrads here? Okay, great. So we have a nice mix. I'll ask more questions about you guys later. I'll start off today by a little bit of an introduction into visualization. That's probably going to be the first half of the lecture. And then I'll move into some organizational stuff. What do you have to do well in this class? How is this class structured? What are the resources and so on? If you have any questions, like I've tried to keep this super interactive. So just raise your hand and just like speak with me and ask questions, and let's have a classroom discussion. This is the first time we're in this classroom, which is a little bit smaller. It used to be on the other side of the hall. And so I think we'll even get a better atmosphere here. Great, so I like to start, like actually most of my research talk plus my lecture with this quote. The purpose of computing is insight, not numbers. And this is by Richard Hamming, whom you might know as a famous computer scientist / mathematician. And what he's saying here is that if you're on a supercomputer and like invest a lot of energy to do some calculations, what you really want is to learn something and not just to get numbers out of it, right? And so some smart Viz people, like 15, 20 years ago, have slightly modified this quote to say the purpose of visualization is insight, not pictures. Again, doesn't seem like a tough statement, right? We really want to create data visualizations so that we can actually understand what's going on with data. But it turns out that's not the most common. Like, you've probably seen a lot of visualizations or infographics out there that weren't particularly informative, especially if somebody who isn't super skilled at creating visualizations is made because they were somehow misleading. So we'll have lots of examples where visualizations aren't that great, but I would just like to show you one that I've kind of encountered in my research. So let's suppose I am a biology researcher and I want to analyze the evolutionary relationships of these 6 different plant species. They're all pretty standard food plants. They have Latin names, and then if you want to understand how are they related, a simple way to do that is simply to count how many genes do each of those plant species share, right? So you could say if banana and date share like 97% of the genome, they're probably very, very similar. And we do these analyses like all the time in biology. This is the picture that the authors of this paper in Nature have come up to visualize this data set. I call this the infamous banana Venn diagram. So can anybody tell me which plant species do have the most common? You're not supposed to get the answer. That's why I'm showing you this picture here. So like Venn diagrams, like set intersections are really hard to visualize, right? This is a 6-set Venn diagram. This Venn diagram was created to say, like, it is possible to draw a 6-set Venn diagram, but this is like a terrible visualization. And notice that this isn't in some kind of like obscure journal. This is like a Nature paper that for the first time introduced the whole banana genome sequenced. Why do you think those authors like chose this picture for their paper?
Made sense to them.
It looks cool. There's a banana in there, right? It's on topic. So, like, basically, what this picture does, it makes their article look a little less boring. So, why is this a bad chart? Let's take a look at up here. Here we have a segment of 1,151 shared genes, and right next to it we have another segment of 40 shared genes. So, there's no proportionality of how important an intersection is to how much of it is displayed on the screen. So that's a problem. The other problem is that we have, like, here's another example of this disproportionality. Here we have a gigantic segment with 105 shared genes. The other big problem about this diagram is, of course, that we have no idea of which sets are participating in a particular intersection unless we sit down with a pen and draw it. And so in this class, we'll be talking about how can we actually create visualizations that are meaningful, that actually lead people to learn something about the data, that they can actually generate insight. So if you look at the dictionary and look up visualization, you will find the definition of the formation of mental visual images, the act or process of interpreting in visual terms or of putting into visual form. So like historically, or like let's say in general language outside of like visualization as a research area, outside of computer science, people think of visualizing things like I visualize myself in my happy place, right? Things like that. But of course, this isn't really what we are talking about. We care about displaying data. And so here's the visualization definition, as you would find it in our textbook by Tamara Mansner. Visualization is the process that transforms abstract data into interactive graphical representation for the purpose of exploration, confirmation, or presentation. So that's a long and winding definition, as it's typical of an academic definition. But a couple of things that are interesting here. First is, like, of course, it's all about data. So this is why, like, this is not computer graphics, right? We're not rendering something fancy that because it looks good. We are really part of like a data science process. We're really trying to communicate data in some way. And data can be like abstract or concrete. I'm gonna skip over this now. We have to transform it very often. Like sometimes we have data that is like at a nanometer scale or at some kind of like very, very small variations, and we usually have to transform the data in some way to be able to reasonably display it. And then we are not here to do like news graphics, right? This isn't an infographics class. We are in like this is a computer science class, and so we will use interactive graphical representations, which we will usually implement in some form. And interactivity isn't just something that we can add on top of the visualization, but interactivity is the super powerful tool that allows us to really like use the visualization to get into details, to investigate a data set much more than a static image ever could. And then finally, this definition contains the three different like purposes of the visualization: exploration, confirmation, or presentation. Like as you probably encounter visualizations unless you like work on your thesis in some applied science field. You probably encounter visualization mostly as in the form of presentation right now. So if you look at the New York Times, they've been doing an amazing job in the last 5 or 10 or maybe even 15 years of creating interactive visualizations for the purpose of presenting data, something interesting to an audience. And so we'll focus a little bit on presentation, like essentially like a lot of the examples that I'll be showing are visualizations created for presentation. But this is like mostly because those examples are very accessible, they're very easy to show, and they're usually created in a way so that I can share it easily with you. But I think a lot of especially academic visualization work is really about this exploration and confirmation step. So what do I mean by that? Well, I'll come back to this a little bit later. I just wanted to reflect a little bit. What is a good data visualization? It's about making data accessible. It's not that this Venn diagram didn't make the data in any way accessible. It kind of like actually hid some of the relationships. Like a table might have been a better way to present this data. One big thing is that data visualization is supposed to combine the strengths of humans and computers, right? Computers are great at like whatever, like calculating things, storing, retrieving information, like making predictions based on models and so on. But humans have, like, we have this amazing ability to perceive like a picture and really understand relationships much better than a computer can in many cases. So we can kind of leverage both of the power of computers and of human perception when we have a good data visualization. And everything is about enabling insight, really understanding something new about your data set and about also communicating. Like if you have understood something, you want to share it with somebody else and make them understand. So this is Stu Card, who is like a famous Vis professor, and he, like, I think this is a very like insightful quote here. Visualization is really about external cognition. That is how resources outside the mind can be used to boost the cognitive capabilities of the mind. So what does he mean by that? Yeah?
Making it so that people's brains don't have to work as hard and look at information to get the result they're looking for.
Exactly. So you could, in theory, like read in a long table, memorize it, and try to find all of the correlations in that particular data table. But if you plot it and have like an artifact to look at, you can use it as this external tool, like outside of your mind, to boost your cognitive capabilities to understand something. So why do we visualize data? Well, first, of course, is to inform humans for communication. So for example, if we ask a question like, who is ahead in election polls? Then we can also use visualization when questions are not well defined. Then we want to go more into this exploration. Like this is really just like visualization for the purpose of communication. But if you have something like what is the structure of a terrorist network, or which drug can help patient X, like there isn't really a clear answer, right? We can like look at many different data sets, we can look at data sources we find somewhere and try to synthesize something and learn something. So this is really the explorative piece about visualization. So here's like a continuum of this like exploration to communication. So here's a tool that we built a while ago to like look at gene expression data for cancer patients. The goal was kind of like to help scientists understand, are there, like let's say you have lung cancer, are there subgroups of lung cancer that like respond different to certain treatments, right? So that we could give, like basically, if you go towards precision medicine. And this was a super interactive tool where people could use like combined like algorithmic methods, clustering, and then judge the quality of outputs of these algorithms and see what the outcomes are. I don't want to go too much into details here. On the other hand here, like this is a chart that has been published by the Obama campaign back when he was up for re-election in about like 2011. And so this chart was really created to communicate, but also to influence, right? There is some bias in here. So what does this chart show us? It shows us US job loss. Notice that, like, this is, by the way, called the bikini chart and is extensively discussed in like various visualization-related blogs. And so what we see is essentially job loss under Bush on the left and under Obama on the right. And so you can see first they chose to like show job loss as bars pointing downwards. And they have these very dark red for the Bush administration. And then under Obama, we see there's actually still, by the time he runs for re-election, there still wasn't like only 1 month or one time point here where there was actually a job gain. So the economy was still bleeding jobs. But they made it look like it's going up, and it did in fact go up, right? But they chose this very, very like consciously, like under Bush going down, under Obama going up. So this is a chart that's really created to communicate, but also not completely unbiased, although you could argue that the data here is at least somewhat fair. But, well, did they have to pick that cutoff point for the Bush administration, right? Or could they have gone back before the financial crisis? Maybe that would have been quite a different picture. We'll be talking a lot about these like trade-offs and how we can communicate faithfully. Here's another example of communication that I think works really well. So who here is interested in football, like even tangentially? Not a lot of domestic students. Okay. So this is a visualization from the New York Times that showed us why Peyton Manning's record will be hard to beat. This was kind of like the all-time NFL touchdown passing record. So you see here, like this is an interactive visualization. So I can hover over all of those people. I can see like when did they start their career and how many touchdown passes did they complete. And you can see essentially what they did very smart here is they kind of made an editorial decision of a couple of interesting people to highlight, right? Basically, they always highlight the best people at that time. So here, Sammy Bow or like Johnny Unitas or Fran Tarkenton and so on. And so you see like how long it took those people to achieve these certain records. And then you see the people that the color is used very consciously here to highlight all the people that are currently active. So essentially, Peyton Manning is the bold one, everybody else is currently active, and so these would be the people that could potentially still beat his record because they're still playing, right? But what you also see here is that he has like an extremely steep progression of like completing his touchdown passes. So it's going to be hard for other people to kind of catch up to that. But there is people like Tom Brady, like this is a little bit outdated from 2014. I don't know what the current situation is, but he potentially has a chance to catch up, although his record isn't quite as steep. So this is a visualization very carefully crafted for you to really like see the point that the editor wanted to make. So this is all about communication. So I'll skip over this. I talked a little bit about this. So why do we use graphics? Why don't we just like calculate the answer in some way, right? And of course, calculating the answer is sometimes a super viable option, but sometimes it's not. So first, like we have like our sensory bandwidth is very different in terms of like are we like touching something, hearing something, and so on. So like our auditory perception is mostly linear, right? We're not good at hearing multiple people speak at the same time, whereas our graphical perception is super parallel. So we can see like the gist of a big scene. We can very quickly recognize outliers. We have certain like properties that we can use to make things pop, to like pre-attentively let people discover them. And all of that essentially is thanks to like how our visual system has evolved. And so we have this like amazing bandwidth. And of course we also want graphics because figures are richer. They provide more information with less clutter and in less space. Figures provide what's called the Gestalt effect. So that basically they give us an overview. They make structure more visible. They're usually more, the sum is more than its parts for visualizations. And of course also figures are, there's a bit of a lag here. I see more than you. Okay. Figures are more accessible, they're easier to understand, they're faster to grasp, they're more comprehensible, they're more memorable, and there's research that shows that visualizations can be very memorable, they're fun, and they're also less formal, right? So like if you have a great piece in the New York Times, people will first look at the figure and at the visualizations and then start reading a text if they're interested. So here's an example. I kind of like, this is from, like, many of you probably know the New Yorker, right? The New Yorker is, like, at least for me, notorious for not using any figures. So they use, like, they have cartoons, and but they don't barely show photos, and they don't show any graphics. So I want to read to you this one paragraph here. Compelled and switched to an identically constructed map, only this time based on 2010 census data. And in bits and pieces on the screen, there was a simple and arresting picture of what Katrina meant. In the neighborhoods that were once dense black, many of the little squares had thinned and turned gray. The sharp lines that once separated the teapot from the central city were now blurry. The white areas of the city were pushing north into the vacuum left by the exodus. The bywater was graying as the gentrified still further. Before Katrina, an American community survey estimated that New Orleans parish population was 455,000, and about 68% black. Now the last estimate is 384,000. So what you have here is a paragraph explaining a visualization. Who kind of like gets what this is about? It's really hard to grasp, right? It's like it's not impossible. You can kind of understand like what is the data here, but it's like not a very efficient way to communicate spatial data. Here's a picture. It's not exactly the same data set. I couldn't find the data source, but essentially this shows us Katrina's diaspora, right? Where do people that were displaced by Katrina now live? And we immediately see where they now live, right? We see that like the most people that were displaced still live in the larger New Orleans region, but we also see that a lot of people moved to other urban centers within the United States. So like the point here is, if you can show something with a visualization, just do it, and don't describe the data in some long and winded way as you had in this New York article. Of course, there are reasons when you do not want to visualize. So one particular important reason why when you don't want to visualize is when you have well-defined questions on a well-defined data set. So if you, for example, ask, which gene is most frequently mutated in the set of patients, and this is all you care about, nothing else, then you can just run an algorithm that gives you an answer that is a single name of a gene, and that's it, right? You have solved your problem. If you want to know what is the current unemployment rate, you can look it up. It's a number. You can run a query. You don't need to visualize that. But how relevant is that particular question, right? What is the current unemployment rate can answer the question you might care about, but maybe you care a lot about what is the context? How did this develop? How was it like 10 years ago, 15 years ago, and so on. Another reason when you don't really need visualization or can't actually use it, if no human intervention is possible or necessary. And usually there's two reasons why you don't want human intervention. Either because decisions are needed in minimal time, like think about high frequency stock trading, That's not something where you want a human in the loop, because by the time the human has seen the picture, the whole thing is over, right? Or if you like were on an assembly line, you didn't want to visualize which of those bottles is broken, you kind of like want a system that automatically identifies a bottle and it just throws it out. But also sometimes it's kind of like impractical for humans to be involved, right? If you want to build data systems like your Netflix recommendation service, while it would be cool that somebody curates like your personal Netflix playlist on your past preferences, you kind of like need some automated methods to do this at scale. So there are certain reasons why you do not want to visualize data, and you'll be able to identify them pretty quickly. So here is an I like to this is the ability matrix of humans and computers. So as I mentioned before, humans and computers have complementary strengths. So for example, computers are really great at precise data storage. They're great at numerical calculation. They're great at searching and finding. They are somewhere okay with logic, right? They can basically execute logic, but they're it's more difficult if you have to really derive anything themselves. Planning, diagnosis, prediction is kind of like where human strengths really start to take off, and then especially cognition, common knowledge, and creativity are things where humans really surpass computers by far. And kind of like, especially when you talk to scientists, you will always find that this common knowledge piece, the data that's not encoded somewhere formally, that they have as part of their education or part of like how they design an experiment, that is kind of like why you need the human in the loop. Another reason to use, why do we use computers? Why don't we just draw everything here? Of course, there's like multiple reasons. First, we some things are really hard to do by hand or even Illustrator. It's infeasible or inflexible for updates. And like if I asked you to draw an MRI scan, like that would be really hard, right? You do not want to do that. So you want to use a computer that you can put in a data set and use some kind of existing program to visualize data in some kind of reusable way. The other big reason is interaction. So interaction allows us to drill down into data. So here is like a tool that one of my students implemented like a long time ago. And I don't want to talk about what they're showing here, but it's just like, it's a very interactive system to let you explore a very big tree, and you have a couple of fancy animations that people understand what's going on, you have mouse overs, and so on. All of these operations here would of course not be possible in a static medium if you don't use a computer. And then another thing that is super important nowadays especially is the integration with algorithms, but also making visualizations part of a data analysis pipeline, right? Lots of visualization problems nowadays are really like in concert with like some machine learning application, some algorithmic application. You want to see the output of a classifier, you want to like proofread your models and so on. So there's many, many interesting applications in that space. We want to be efficient, we want to be able to reuse charts or methods for different data sets. Of course, like computers, once you have your code working correctly, you can load every other data set that fits the kind of like preconditions, and you have a precise data-driven rendering. And then you can also use animations and time to tell a story, right? You can do like have a slideshow or create an interactive video with a computer. Here's like a data visualization that is almost a video. So let me see how the audio here does.
Hitters with mostly one pitch, his signature cutter. John Flaherty of the Yes Network faced Rivera as a hitter and also caught him when he played for the Yankees. Mariano Rivera is one of the most dominant closers in history. But what may be most remarkable is that he has done it by confounding hitters with mostly one pitch, his signature cutter. John Flaherty of the Yes Network faced Rivera as a hitter and also caught him when he played for the Yankees.
From a hitter standpoint, he's out on the mound. It feels like he's not even putting any effort into it, and the ball explodes on you. And from a catching standpoint, he's the easiest guy ever to catch because he throws the ball right where you want it. Rivera uses a seemingly effortless delivery, which he can flawlessly repeat, pitch after pitch. His cutter is thrown very much like a fastball, but the pitch has significant lateral movement. He creates and adjusts this movement with the different pressure he puts on the ball with his fingers. The pitch's lateral movement keeps it off the bat's sweet spot, moving in on the hands of a left-handed batter and toward the end of the bat of a righty. To a hitter, Rivera's cutter first appears like a straight fastball,
making it hard to distinguish the two pitches during the first fractions of the second when the hitter must decide if, when, and where to swing. Hitters often rely on reading a pitch's spin to determine what pitch is coming. Pitcher, while Rivera's fastball and cutter have what appear to the hitter as the same spin. Many pitchers throw their cutters more like sliders, with their fingers pulling down on the side of the ball. This can create more downward and lateral movement than a cutter, but it also creates the signature spin of a slider, a spinning red dot, that the hitter can recognize and adjust to. With identical deliveries and spins on Rivera's pitches, hitters are at a loss to identify and then attack the pitch, until it is too late, and the balls end up in very different locations. Here are the nearly 1,300 pitches that Rivera threw in 2009, each frozen at the point when the batter must make his swing decisions. But with few clues to determine the pitch's ultimate location, the batter can be faced with guessing at these outcomes. Here are the cutters to left-handers. Here are the cutters to right-handers. And fastballs to right-handers. He throws almost no fastballs to lefties. As this map of his 2009 pitches shows, Rivera is remarkably adept at hitting the corners, keeping the ball away from the middle of the plate, the easiest spot for a batter to make good contact.
Looking from this perspective, it's not surprising that the real hot spot is inside on the lefty. I think he could hit that spot with his eyes closed.
Rivera's simple but effective formula has made him baseball's most dominant closer.
Yeah, so this is an example of a really well-told animated data story, right? There's like some concept in here of like, of course, storytelling with video, lots of computer graphics, but then there's some basic influence principles or visualization principles encoded here as well. So some of you might think, well, why don't we just use statistics, right? We can maybe kind of do some we can build some smart model or use some kind of like simple descriptive statistics to calculate the answers that we care about. And like you'll see many reasons why this isn't always the case, and you should always look at your data, but here's a very simple example. This is a data set that is constructed, this is called Anscombe's quartet, and so you have 4 different data sets here with 2 dimensions each, x and y. And so if you look at this table, it looks like there is some variation in here. You can see that data set 4 is a little bit different because there's all 8s in the x dimension except for 1. But otherwise, it's really hard to get to understand what's going on in this data. So what we can do is we can calculate some descriptive statistics. So if we say, like, what's the mean in x? It's 9 and 7.5. And the interesting thing is this is the same for all of those 4 data sets. It's also true that variance is identical for all of these data sets. The correlation is identical, and the linear regression is identical, right? So if you just ran these like naive statistical, like descriptive statistics on this, you would conclude those 4 data sets are identical. I can proceed with my analysis. However, if you plot them, this is what you don't see. This is like I'm using this AirPlay video presentation for the first time, and there seems to be some lag. So if there's ever anything that I'm talking about not on the screen, just let me know. So what you see here is like here you have like a linear correlation with some noise, kind of something like you would expect. Here you have a non-linear relationship, and then you have 2 examples of the effects of outliers. So clearly those data sets are not the same, yet they have identical statistical properties, at least in these simple statistics. And so what we learned from that is that even if we want to use some statistical modeling later, we always need to look at our data and just see that it passes the smell test. This is the dinosaur and dinosaur scatter plot here, and you have certain like mean and standard deviation and correlation variables. And this was a paper from 2007 that introduced a method that can fake these like mean and standard deviation values for like pretty arbitrary transitions. Notice that like even the intermediate steps here have the same statistical measures. So like this is like just basically by smartly like basically these are adversarial examples for basic statistics. And so you always have to really look at the data to know to be able to trust it. So the way I think about visualization, and I think our lab generally thinks about visualization, is it's not about rendering pictures. It's about human data interactions. Like how can humans interact with data so data can understand what. Visualization is really just a mean to it. And it's the best mean we have for that. But what we really care about is that human can efficiently interact with their data. So, like you're probably like, oh, like everybody is aware of like this big data science hype and the big AI and machine learning hype, right? And so where does visualization fit into this whole process? This is a figure from Rachel Schutt and Kathy O'Neill's book that's called Doing Data Science. And it's kind of like a process diagram of how like the data science process works. So you have the real world. Something is happening in the real world that you want to observe. You collect some data about it. Then you process the data about it. Then you clean the data, right? Like data is never initially clean, so you have to always do something to it. And then you do some exploratory data analysis. And this is where you really like can like leverage visualization for the first time in where visualization is really your main tool. Like kind of like what is in my data in the first place, proofreading, sanity checks, and then kind of like deciding based on that what are my next steps. Then you could build build some statistical models or run some machine learning algorithms on it, which would then create some output, which you need to communicate and report findings. And this is again where you can use visualization, right? Like at the end of some kind of analysis pipeline, you can again use visualization to communicate your results. And then if you have like a workflow where you need a human to make a decision, this is where they would make a decision. Of course, you could also build a data product, like for example, your Netflix recommendation system, where you don't really need a human to make, or at least not an analyst to make a decision, where you would have something like a data product that impacts the real world in some way. However, in recent years, like visualization has kind of permeated many of those intermediate steps. There's now like data cleaning companies like Trifecta, for example, that use visualization combined with machine learning to make data cleaning and data processing much more effective. If you want to build a machine learning model, you probably want to use visualization to understand what's going on in the first place. So like these two are just like where you really need visualization, but visualization can be a part of other parts in this pipeline. And then of course, like this is a data lecture, like a lecture about data, and so of course I have to tell you how like omnipresent data is nowadays. I like this like XKCD comic here that showed you if we had like there's about 15 exabytes that in existence like back when this comic was made, and if you were to store this in punch cards, it would stack up 4.5 kilometers over New England. Just like to have a practical point of comparison. And in 2017, 2.5 exabytes of data were created per day, which are largely unstructured, and 90% of the data was created in the last 2 years. And of course, if you like Google YouTube cat videos, you get about 590 million results. It's just an example of how much data that's out there. Here's a tool that actually shows you like, what's going on the internet. So in 1 second on the internet, there's 8,000 tweets sent. I'm scrolling here. Then we have Tumblr posts, which is kind of like not very big anymore. Then we have Skype calls. Then gigabytes of internet traffic in 1 second. And probably most of this is Netflix. Then we have 76,000 Google searches in 1 second. And I'll have to like grab my slider here. And then here 80,000 YouTube videos, and then 2.8 million emails sent, and more than half of it, the black ones here, are spam. So just like how much data is being generated. And I could keep scrolling here, but it's going to be very boring. Data can also be super personal, right? This was just very generic. Here is some personal data about myself. I took those, like some of you might use things like Runkeeper or Strava. You have a GPS log of like where you've been, where you exercised. You can see like what your heart rate was, what your speed was, what your cadence was. All of this is collected, and that you can use then to visualize your data. Or you could have like longer term, like if you have an Android phone and you haven't explicitly opted out, Google actually collects very precisely where you are, and you can look that up, right? So this is just like, I didn't actually plan on this. I just looked back on a day where I like went home or started at home, went to work, picked somebody up at the airport, went back to the city to have some dinner, and then went back home. And not without me consciously coding anything, this was the trace that Google created, just by me carrying my phone. And you guys have this data probably available in your pocket right now. So data can be very, very personal, in addition to the data that everybody can get. In science and engineering, big data has really transformed lots of things. I think it's fair to say that a lot of scientific disciplines are nowadays moving into database sciences. When back 10 years ago, 15 years ago, let's say a biology student probably didn't have to know about Python or R. Nowadays they have to. Nowadays they really have to learn how to handle data on a computer. So there are examples of large physics experiments and observations where we have terabytes of data. We have genome sequencing. This is here a graph of the cost per megabase of DNA sequencing. And you can see that the line on top here is Moore's law, which kind of shows the increase of the number of transistors over a certain period of time, which is logarithmic. Here we have the cost per megabase of a DNA sequence plotted against this on a logarithmic scale, and you see that essentially it's now almost free to get your DNA sequence, right? And that's why we have companies like 23andMe and Ancestry doing this data analysis, even for consumers. We have smart buildings, we have smart cities. There is a startup company in Salt Lake City, it's called Blinsky, that puts up little gray boxes all over the city. And those boxes are just passive Wi-Fi monitors. And so once you drive by them without you knowing it, your phone simply keeps scanning for Wi-Fi hotspots and it connects to those. They never offer you a connection. They just track that you were there. And then they can build a movement profile without you ever knowing. And they're using this to study traffic flow, for example, during Sundance, and to help them optimize how they could direct the traffic. But of course, there's also tons of implications for privacy, right? They can probably reconstruct in very much detail, who I am, because how many people live in that building and go to that place for work and have dinner at that restaurant all the time. So they can probably identify you quite well if they wanted to, and all your movement patterns without you doing anything actively, just by carrying your phone. We have geophysical imaging, right? We have satellites above us that collect data about us. And of course, in the sciences, we have this controversy about should science be hypothesis-driven, or should it be data-driven? Is it a legitimate scientific approach to simply calculate and look for answers or look for interesting patterns, or do I have to have a hypothesis first, because otherwise I could get come to spurious correlations, or to random events and so on. So we'll talk a little bit about these kind of things as well. Here's an example. The CERN Large Hadron Collider data has publicly released 300 terabytes of data. If you wanted to burn this on DVD-Rs, you would need 63,000 DVDs to do that. If you wanted to stream it on Pandora, it would take you 1,200 years. At 4K video streaming, it would take 98 years. And then the NSA currently, with a big data center in Utah, by 2013 figures, the NSA touches about 300 terabytes of data every 15 minutes, just to give you some sense of scales. Here's an example of genomics, how this impacts the field of genomics. Right? We have these, this is a sequencing machine here. It's as big as a palm, and back 20 years ago, that was $1 billion effort to sequence somebody's genome. We can do, there's various scientific instruments nowadays that can deliver data to us. We can use this to study diseases, to understand evolution, for all of these different purposes. This is the data center that I was referring to. There isn't really any exact data. This NSA data center estimates vary, but this Forbes magazine estimate that there is about 12 exabytes stored in this Utah facility. So the ability to take data, to be able to understand it, to process it, to extract value from it, to visualize it, to communicate it, that's going to be a hugely important skill in the next decades, because now we really do have essentially free and ubiquitous data. This is from a McKinsey report. I think there barely isn't any. Like it's from 2009, 10 years later, we live this, right? This is kind of like what is going on right now. So this isn't a class just about data or algorithms. This is really, as I mentioned, about human data interaction. And so we have to like really design also for humans and be mindful of their limitations, their fallacies, their biases, and so on. And so what are these things? We can leverage human capabilities like pattern discoveries. Like we are great at spotting clusters in 2D, at spotting outliers, at spotting trends. We have, and I think this is the most important piece, we have all the contextual knowledge, right, that helps us interpret what we are seeing. And of course, we are also the people who can take action. If we see something, we can act based on what we learn. But we also have to design for humans and their limitations. Not everything that can feasibly be drawn can also be read. Here are two examples of like very large networks that somebody tried to visualize, and like you don't see any structure here, right? This is just like big hairballs. These are not very meaningful charts. So like we can draw this, but it's not drawn for a human to perceive. And then there are certain limitations in the human perceptual system. And we'll like essentially like this week and next week we'll be looking at some of those things at like human perception, human cognition, and what are the problems with it. I'll just give you a little example here of like this is from a psychology study. This guy here is asking the white-haired and bearded man about directions, and he's giving him direction, and he's completely immersed in the task. And notice what happens next. Switches out the person, and the white-haired man doesn't even notice, right? Because why is that happening? Because he's so immersed in his task. He like we have a mind that can focus on a single thing at one time, and if we like really use our attention for that, we really are very oblivious to everything else that's happening in our environment. And there's many examples of how this is relevant to visualization. We'll cover some of this in the Thursday lecture. So now I want to switch gears a little bit and talk a little bit about the history of visualization. I don't want to spend too much time on this, but it's good to know where we're coming from. Of course, like you have to start an academic class about visualization with cave paintings. So like we like historically, like coming back to this quote, it is things that make us smart, and that's definitely true for like things that we paint and of course writing, right? As soon as we developed writing and books, like knowledge exploded because we now had a very efficient way of passing it on. So it's the things that really made humanity smart. And like historic inkunavels or books like really contained lots of figures back then. Like many of them were illustrations, but some of them were like diagrams, right? Like here's some mathematical diagrams, like triangles, and then also some like music notation or something like that. Here is like the oldest known map. This is of a town in Turkey about 6,200 BC of Konya. So you can see that like perspective wasn't. I think this is supposed to be a mountain, so you can see perspective wasn't like perfectly developed yet. But this is a really old artifact. And then here's a map of the Mediterranean about 550 before Christ, and you can actually recognize the shape of Italy here. You know where to look. And then we like Leonardo da Vinci was well known for like his anatomical sketches. This was used for people to like study like basically human physiology and medicine. Galileo Galilei drew like the moon, and then we had lots of scientists like create sketches of plants and animals and so on to kind of like communicate knowledge and to create these artifacts that others can use to then learn something. This is like a famous series of photographs by Edward Muybridge from 1878. And so back at the time, it was kind of like controversial whether the hoofs of a horse ever leave the ground when it's galloping. And so people weren't sure about this. It was really hard to perceive. And so he set out to kind of like investigate this question and set up a series of cameras that were triggered by a wire, and then had a horse run around this, and then collected those pictures. And then like somebody has on the internet created an animated GIF out of it. And so we can see that in fact the horse here, like all of its legs are in the air. So this question is now answered. Again, like we're an artifact, the visual artifact, like lets us observe something that we couldn't learn before. Little anecdote about Edward Muybridge. He was like Stanford, the guy who founded the university, he was a benefactor, and he actually his wife had an affair, and he did shoot it was a captain, I think, some kind of military personnel. He did shoot that captain, but was acquitted for justifiable homicide. Back in the day, that was the reason. So here are some, like these were all very concrete examples, but then like what we're studying here are these more abstract representations of data, and here are some of these. Like here, there's a planetary movement diagram from about 950, and then wind is also not something that we can immediately see, but we can plot it on the map, and as you can imagine, if you're a sailor, a wind map like this is very useful to you, where you can basically see what are good routes for me to take. And then we get into really statistical graphics. Here you will see a lot of early work by William Playfair. This is kind of like one of like on the early area chart. This shows us the exports and imports to and from Denmark and Norway into the UK. So you can see like a balance against the UK, and then an inversion, the balance in favor of England, not the UK. And then here are some bar charts. And then here on the right is like a very early pie chart visualizing the proportions of the Turkish Empire on which kind of like continents it is, like Africa, European, and Asia. So just like historical statistical graphics. And is anybody like who's kind of like even tangentially interested in visualization has probably seen this chart here. Who's seen that? A couple of people, but not too many. Okay, so this is a map that John Snow, who was a physician, used to kind of like communicate a point. This is London, and these little black bars that you see here are cholera cases. And back then it wasn't completely clear whether how cholera is transmitted, whether it's airborne or whether it's waterborne. And so he made this observation that cholera really is spatially clustered. And so he created this map to communicate his observation. And you can see that like we have here each of these little black bars is a person with cholera. You can see there's like here like a pretty dense cluster of cholera cases, right? And then he plotted the water pumps, the closest water pumps here. And there's two water pumps. You can see the red one and the green one. And you can see there's barely any cholera cases around the green water pump, but there is a cholera case around the red water pump. And the legend, I don't know how much about this is true, it goes that he, based on this map, convinced some magistrate to remove the handle of the water pump there, which helped fight cholera in that area. Okay, then another map that you've that's kind of like the archetypical basic infographic or visualization. This is by Charles Minard. He was a French cartographer, and this shows you like Napoleon's campaign on Russia. So basically, Napoleon was planning to invade Russia, and this like was made famous by Tufte, who is like a statistics and visualization professor now, retired from I think Princeton. And so what this map, like what the Tufte called the greatest map or the greatest data visualization ever made, shows is like Napoleon set out with an army, and here the size of this ribbon here encodes the size of the army. And he kept marching towards Moscow. And what you see is that he, on the way there, he kept like losing troops to like either skirmishes or to like environmental factors. And then he like had the Battle of Moscow, and you can see that like the black flow here is actually the retreat. And you can see that basically the brown and the black one are almost the same width. So the actual like main battle didn't cause that many casualties in the first place. But then it was winter, and then for like the retreat, he also shows us temperature here on the lower, like in the line chart at the lower end. And so you can see that the temperature was getting really cold, and that here we have some certain river crossings, and then here we have a river crossing, and then here we have another river crossing. And at this particular river crossing, it was really like minus 11 degrees Celsius, and a lot of people drowned in that particular case. And so you can see that Napoleon then eventually returned with a fraction of his army were, like most of it wasn't actually lost in the main battle. This is just a link. I don't want to go into detail here, but this is a link of a collection of some interesting historical data visualizations that you can browse at your own later. It's like interactive, so you can go there. There's like nice figures, and then you can like look at it and get some more information. Who has published this this particular figure? This is like not, of course, a complete record in any way. There are great books out there that collect these historical graphics, but this is like a good starting point if you care about that. Geospatial maps are very common. Like here's a subway map. This is the London Underground, and so like what you like see in these kinds of maps is very often like a compromise between visualizing the structure of the network of these trains and visualizing geography. So here, really, the purpose is to like get people oriented and to give them a little bit of spatial context as well, which is kind of like a common way to think about a subway map. Here's an alternative encoding that again you can see. Yeah. Here's an alternative encoding, the Boston subway map. So here we're kind of trying to make a compromise between geospatial encoding. So we still have the Charles River as a main point of orientation, and also like it nicely fans out from the city center, but the distance to the center is actually time. So you can see how long it will take you and not how far it is to go there. And if you've ever been to Boston, you know that the green line is super slow compared to the red line or to the blue line or anything like that. And so this isn't actually that far. Alewife is probably further out than the green line here, but it will take you forever to go there. So like you don't always have to encode space in space, but sometimes you can do things like encoding time in space. And then we get into a little basic human-computer interaction. Like we now have these super powerful computers. And where did this all start? I'll show you two videos here. Ivan Sutherland, who developed this tool, Sketchpad, while he was at MIT, but he was later also Utah faculty. And then Doug Engelbart, the mother of all demos. And I'll just show you a couple of minutes of those videos. I'll share the slides later. Those are pretty long, but pretty amazing to look at. So if you have some time, you take a closer look at those.
Forego when I from this position where I am now to any subsequent position of my lifetime. This is much like a rubber band stuck in two pins. One is nailed on the screen here, and the other is at my lifetime. So I can position this anywhere I want. Now, I lost track of this.
The lag is not
the computer to stop drawing the line. Well, if you notice, that bright dot will jump onto the line as I get close to it. When the dot in the center of the cross, when you get close to it, it jumps over.
Yeah.
Gravity field at the end point is even a higher gravity field. It allows us to position the point exactly on the line, or in this case, exactly the end point. This allows me to move my pen quite coarsely. Keep sloppy while I'm drawing, and get a precision drawing on at the same time. So now I'm going to draw the second line. There we go. And even the third one. Now, in an ordinary pencil and paper drawing, all we have is this particular picture. But the computer understands the geometry of the drawing here. What do I mean? I mean that if I point at this particular point and tell the computer to move that point by another push button command, it will move not only that point, but all three lines that are attached to it.
And the delay between doing what you want to do is because computing always changes.
Early example of an interactive graphic, right? Like this
Now,
was a super famous system.
I could delete my
back in the
mistake. I point
60s.
at the line.
And so this like goes into like basic CAD editing. And then here, this other demo, the mother of all demos, which is this is actually like a 1 hour 40 video demonstrating like a load of different technologies here, including hypertext video conferencing, the first mouse. And so I'll just play like 2 minutes or 3 minutes of it.
Keep track of where we are, and a little bit to help me too.
We'll move that down. So, having gone through these items, I'd like to come in now and begin to tell you something about the implementation. So I'm going to open up under here and talk to you about the control techniques, control devices, control dialogue, and control meta language that we're using. Okay, to talk about control devices, we'll use this overhead camera shot. Well, you can see the devices that I'm using. I use 3, and they're not all standard. We have a pointing device called a mouse, a standard keyboard, and a special key set we have here. And we're going to go for a picture down in our laboratory in Menlo Park and pipe it up. That'll show you from another point of view more about how that mouse works. Come in Menlo Park. Okay, there's Don Andrews' hand in Menlo Park. And in a second we'll see the screen that he's working and the way the tracking spot moves in conjunction with movements of that mouse. I don't know why we call it a mouse. Sometimes I apologize. It started that way and we never did change it. As it moves up or down or sideways, so does the tracking spot. And the principles for its operation are quite easy to see. You'll turn it over, Don. Can you hear me, Don? Let's turn it over and we'll see. Right. This principle is that there are 2 wheels that work on the surface. There's right angles and kind of sharp edges. One roll and the other slide in one direction. Each of these wheels controls the potentiometer with a voltage output, sampled by an AD converter.
Okay, so these are 2 examples of really early input devices, right? The one, actually a touch pen, and then a mouse. And of course, we leverage systems like these nowadays all the time when we interact with computers. And we can leverage these kind of input devices when we build interactive data visualizations. So let me give you like a modern example, like a couple of fun ones. Here we have the baby name wizard. So it turns out that if you look at names over time, there tend to be like fashions and trends. And so here we have like a stacked area graph of all the top 1,000 most popular names in the United States. And so what you can see immediately is like overall we have like a downward trend that means basically that probably people pick more names that are not in the top 1,000 names. But then you can use interaction to kind of like focus on something. So I'm putting in my name, Alex here, or I'm Alexander, like just a short form, and it says automatically completed a search and retrieved all of the names that have Alex in it. And so you see Alex, Alexander, Alexandra, Alexandria, Alexis, and so on. And you can see that like Alex really peaked in popularity, and I was born around here, so my parents weren't super creative, right? So they picked a fairly popular name. Anybody want me to put in their name? Daniel. Daniel, are you born like late 80s? 95. So downward slope. Your parents like are not a bit as a fashion. Keith, K-E-I-T. Keith, like had a big bump in the 1960s, right? So if you put in some like very like traditional names like Joseph. Now I wanted to like know a little bit about you guys. So let me just pull out my name. So I asked first year, anyone already? Like who's new to Utah as well? Show of hands. Okay, not that many people. New to the United States? Okay, a couple of them. Welcome. Who is an undergrad? Who is a grad? Many grads. Who is a PhD student? Like about half of the grads are PhD students. Who is like CS concentrator either in like undergrad or grad? Should be most of you. Who is not? Okay, so other areas, like who's from math? Yeah, cool. Stats, or well, math and stats is here. Humanities, social sciences, biomedical, informatics. We usually have a couple of people. Some other engineering discipline. Okay. Anything else that I missed here? Got everybody, great. Technical question, who knows JavaScript? Okay, that's like majority who doesn't know JavaScript. Okay, you guys are gonna have an interesting time the next 3 or 4 weeks. And C++, Java, or Python, any of those programming languages, like most people should have any. Who has done like visualization before? Like, yeah, a few people. Great. It's gonna be an interesting class. We'll have a lot to discuss. Great. So, what is the structure and the goals of this class? So, what we want to teach you is how do you efficiently visualize data. One thing that is like before you can create yourself is evaluation and critiquing. We'll spend a lot of time critiquing visualizations, and this is going to be a little bit weird maybe for people who are like come from a classical CS degree. This is going to be a little bit more like a design course, right? We will be talking about visualization. I will ask you to analyze them. I would ask you to think about what you could make better. I'll ask you to sketch and draw and design on your own. We do, like there is a science to it, right? We have like the fundamental understanding of like how human perception works. And so we will learn how we apply these fundamental principles, either empirically studied principles or some principles that we know from practice. And then, of course, we will design our own visual data analysis solutions. And the secondary goal of this course, like this is really like what I care most about, right? That you understand how to design visualizations, but we'll also give you the skills to do this on the web in an interactive way. So we'll be like, especially in the first half of the semester, we'll spend about half of our time talking about technical issues, like how do I actually implement those things in JavaScript in the library that's called D3. So, like as a side benefit of this class, you will become awesome web developers. At least front-end web developers. I'm promising too much, looks like it. But anyways, this is going to be like a heavy piece of this course. And so we have these course components. We have lectures, where basically it's me introducing theory, and in the lectures we'll barely have a lecture where there isn't some kind of activity, where there isn't a design critique or some sketching exercise or anything like that. So here I want you to develop an eye for visualization design, critiquing, and learning by examples. We'll have labs or sections where we will introduce homeworks and go over some technical things, repeat them essentially from what we had in lectures. Those are going to be Wednesdays at 6 in a room close to here. They are like basically if you feel comfortable, you don't need to show up there, right? This is supposed to be the lecture is supposed to teach you everything you need to know. If you want some time to reinforce this, you can go to those labs. The homeworks are really here to help you practice mostly technical skills. Like it's really tricky for us to create homeworks where we can like do technical things and also test for visualization design expertise. So it will be mostly technical specific skills, and then your final project, which is kind of the most important piece of your grade, will allow you to kind of bring all of it together. Like everything that you learn in theory, everything that we discussed in the course, you will design your own visualization in a team and create a complete data visualization project on the web. So this is kind of like where all of this synthesizes in the end. So we have the 3 components, design, theory, and coding skills, and we will capture them in design lectures or like design critiques. And then we'll have labs, we have readings on D3. There's going to be like a fair amount of self-study, right? If you don't know JavaScript yet, I've spent 1 lecture in introducing JavaScript. And so this is going to be a fairly fast introduction. If you know JavaScript, it might not be the most interesting lecture for you, but I also I realized that, and I try to make this class open to like students not just from core CS. So maybe for like the CS concentrators here, the next like 2 or 3 technical lectures might not be the most exciting thing ever, but it will level the playing field so that everybody here can participate. And then in the theory, it's really about lectures, readings, and discussion. And so you'll see that I post readings on a schedule, and sometimes I also ask you to like really read them because I'll ask you to discuss it in class and I'll point at you and then ask you to summarize them. And the grad students here will also have readings on the test. The schedule is on the website. So we have like the schedule, basically the content schedule is like in HTML, and then we have a Google Calendar where you see all the office hours and the lectures in the rooms and so on. So you should kind of like, if you use Google Calendar yourself, you can just add this to your own calendar and always see what is going on for this class. We keep this up to date. if we change an office hour, sometimes somebody's traveling, right? We will update the schedule and put out an announcement. We do have a YouTube channel, so you see the little camera up here, which seems to be working intermittently today. But like this is a new system, we'll get it figured out. You can review those lectures at home. You can go over them. If you missed anything, or if you have can't be here for occasionally, you can review it on YouTube. And the link is in the slides, but also on the website. Kind of the website is your main piece of information, datavizcourse.net. And I really would like everybody to look at the syllabus, also look at the fine print in the syllabus. It's important. I'll come back to some of this in a second. But especially look at the project description here if you want to plan ahead for your project. There's a companion course. So we 3 years ago we decided we have 7 or 8 visualization faculty and a lot of students that are in visualization graduate programs. So we decided it's time for us to offer multiple visualization courses. There's now 3 visualization courses. There's this one. This is the visualization for data science. So here we talk about abstract data. Then there's the basically tables, graphs, networks, and also maps. Then we have this visualization for scientific data, where it's about spatial data, like 3D volumes, flows, fluid flows, or geometries, or anything like that. That will be offered in the spring. I see it's 6635 or 5635 by Valerio Pascucci this year. Yeah.
You said there were 3.
The third one, sorry, is advanced data visualization, which I don't have slides for. That's by Bei Wang, and that kind of covers very large graphs and some kind of geometric methods. I'll put out, and you should take this course or Valerio's course or my course first before you go into the advanced data visualization course. I'll give you more details about that course at the end of the semester. It's going to be offered in the spring. Okay, how can you communicate with us? We use Slack. This has worked great in the past. Please use Slack for all general questions. If you have a question about how something works in code, please post it on Slack. Please do not post solutions. Obviously, ask questions that can help you figure it out. Please don't use personal messages to me or the TAs. It's a big class. We have about 90 students. We get way too many messages. The way this works is if we can't help you with what you can post without showing us your code, a TA will say, please send me a private message. And then you can actually exchange code if you need to, but please don't cold message me or the TAs. You're welcome to cold message me on anything related that's personal in some way, I'm sick for this lecture or anything like that. But please use email. I guarantee you, I really promise you, I will definitely respond on email. I might see your Slack message, but I might not respond at the moment, and then I'll forget. So email always works, and please don't use Canvas messaging. Those, I promise you, will not get a reply. We use Canvas only for homework submission and grades, so all of the information is either on the website or on Slack. Slack has an announcement channel that you kind of need to listen to. This is kind of binding if we announce classes canceled. It's going to be in Slack. But homework submission and grades will be through Canvas, and also we'll try out Teams this year for the first time. And then we have office hours. So my office hours are Tuesday after class for an hour from 2 to 3 in my office, 3 floors up or 4 floors up from here. And then our TAs are where you should go if you have technical questions. For me, you can come with technical questions, but I would prefer if you come with me hey, I haven't gotten this material that you talked about, or I am interested in a research project, or I have a problem with the class or with the grading and so on. These are questions where you can come to my office hours. And if you need help with your homeworks and so on, you should primarily use the TA office hours, which we'll start offering next week. And I'm doing office hours today already. And then my email address is here. There's 2 required books. Both of them are freely available online if you're on campus and have a campus login. This one is a fairly quick read, so I definitely recommend that you look through this. And this one, we looked through a lot of chapters. This is a great textbook, and it might be worth getting a hard copy if your visualization is probably something that you want to do beyond this course. We'll program in, as I said, HTML, JavaScript, and the library called D3. So now, let me just see whether there's anything. Yeah, let me just do something. I'll skip over this. I just want to mention two things quickly. We have only 2 minutes left. A, we have a code of conduct. So we're committed to providing an inclusive and harassment-free environment in all kinds of interactions and regardless of anything, basically. So we kind of like really want to emphasize this. We do not tolerate harassment in any form. There is a way to report harassment. You can come to me, but you can also come to like an anonymous instance. If you find these resources at save.utah.edu. There is much more detail than I can show here on the syllabus, which you can find, and there is also like a student code of conduct for every University of Utah student that you can find at this link. And then one thing that I really want to say, because it's so painful every year, is cheating. Like here is the details, but essentially, like you know what cheating is. If you copy something, A, will catch you, and B, you'll fail, and C, you'll get like we'll put a file with the School of Computing, right? And if you do that 2 or 3 times, I don't know exactly, but I think by the 3rd time, you're out of the program. And I catch people every year. Last year, I caught somebody when they submitted homework 6 at the end of the year. So basically, they lost a complete semester of work, and they had like a have to fail. Everybody who cheats in this class, it's usually not hard for us to prove it. There's automatic methods. So if you like, don't use anybody else's code, don't like copy somebody's code verbatim. You're encouraged to work in teams, to ask questions, to help each other, but do not ever copy anything. We'll catch you most likely, and it will be not very pleasant. It's really unpleasant for you. It's also really unpleasant for me to have these meetings, to have these discussions. So really, please do not do it. Here's the details on what that means. There is the cheating policy from the School of Computing. We are very strict with this. So please really respect that. And like, you do not want to fail this class for some bizarre reason. I'll basically just conclude, and I'll go over some of the stuff that I skipped over today. I'll basically conclude by saying on Tuesday we'll be talking about perception, so human perception, and then Thursday, and then next week we'll start with the technical content on Tuesday, and then we'll always have Tuesday lectures technical, Thursday lecture theory. That will be going on for 6 weeks, and then we'll be basically moving into all visualization. Thank you for being here, Scott. Thanks for coming, and see you Thursday.